Log on, tune in, find out. Another good idea from Cambridge.
Much. I would like to thank the organizer of this organizers of this program for giving me the chance to participate and to give this talk here. And of course, I would also like to thank the people who give the money to support this wonderful place. So I'm going to talk about joint work with Alex Zaleski and Jian Bai An, and also there are some contributions by Olivier Brunat. So I think I will summarize about 3 papers which were written on this topic in recent years. Okay, so let me start with introduction. Well, restricting representations from a group to subgroups is an established and very powerful tool or method in representation theory of groups, not necessarily finite groups, which works particularly well if you know for one subgroup at least much of its representation theory. So for example, if you consider series of groups like Sn, where n is an integer, by way of induction, you pretend that you know everything about subgroups of the same series, say Sn minus 1, contained in Sn. And then you can work by induction. And in this situation, to realize an embedding of Sn minus 1 into Sn can be done, for example, by looking at the natural action of Sn on the set of n points and taking the stabilizer in Sn on one of these points, say the point n. Now I'm interested in classical groups, finite classical groups, and so the analog of such subgroups are vector stabilizers, where the vector space is the natural vector space for the classical group. Okay, so what do we know about representation theory of vector stabilizers in finite classical groups? So let me give you some examples. Okay, well, the first example which comes to mind is you take the general linear group. So let me write G and also indicate the dimension of its natural module to be GLNQ, acting on the vector space V, which is n-dimensional and which we may think of to be FQ to the n. We are talking about finite classical groups. And let me think of these as column vectors. And let's take P to be the stabilizer of, in G, of some vector V0. And to be specific, let's take V0 to be the first vector which comes to mind, say the first standard basis vector. And then what is P? Well, it's well known, of course. P is consists of matrices of this form. They have the first standard basis vector in the first column, and then any entries here, and an invertible n-1 by n-1 matrix here. So this is also can be written as in its Levy decomposition as U times L, with L consisting of the matrices of the form 1, 0, G, and then G is an element in Gn-1. So here again you have a subgroup which is of the same type as G. So this is Gn-1, but of one dimension less. But of course you also have U, and U is the unipotent radical of this parabolic subgroup consists of matrices of this form: 1, 0, 1, and some vector v, where v is in Vn minus 1. And you may think of this as being isomorphic to Vn minus 1, but if you really want to be more sophisticated, maybe the dual space. Okay, so what are the characters of this parabolic subgroup? Well, that's easy. U is a normal subgroup in P, so we are using Clifford theory to describe the irreducible characters, and today I'm mainly talking about ordinary, complex, irreducible characters of a finite group. So we have three types of characters. We have type 1 characters with U in its kernel. So these are, of course, then by way of inflation in bijection to the irreducible characters of Gn minus 1, which is a group of the same type, and you know by induction you know everything about this. We have type 2 characters. We have which have U not in kernel, and these characters are in 1-to-1 correspondence to the irreducible characters of a group Pn minus 1, which is the same parabolic subgroup as P, but inside the group Gn minus 1. Okay, so you have these two types of characters, and to see this, you may just view Pn minus 1 as the stabilizer in Gn minus 1 of some irreducible character lambda, of a suitable irreducible character lambda of the unipotent radical U, which is not the trivial character. So this gives you a classification. This is what I want to emphasize. A classification of the irreducible characters of this vector stabilizer. Let me give you a slightly more complicated example. So this is what Jianbei An and myself have been working on. So this GRH is not standing for generalized Riemann hypothesis. These are my initials. Okay? So this is without a strong assumption. Well, Gn, Sp, 2n, Q, Q odd. Again, now we take V to be the 2n dimensional vector space. We have defined some symplectic form on Vn, and we take P, the stabilizer, in G of V0, where V0 is as above. And then again, we have a Levy decomposition U times L, with L isomorphic to Gn minus 1, which is Sp2 n minus 1 of Q. And U is slightly more complicated with respect to a suitable basis. U consists of matrices of this form: V star 1, Z, 0, 0, 0, 1, V, where V is in Vn minus 1, 2 dimensions less, and Z is in Fq. So this is isomorphic to a special P group. So P always is the underlying characteristic, so Q is a power of P. 1 plus 2n minus 1, a special P group, also called the Heisenberg group, associated to the symplectic form beta, which acts on this Vn minus two-dimensional vector space, a 2n minus two-dimensional vector space associated to beta. And of course, V star is determined by this vector V. You take, it's the, well, the linear form which is obtained by this V. The center of U consists of the matrices of the form, the center of U consists of the matrices of this form, 0, Z, 1, I can omit these, of this form. And it's, of course, isomorphic to the additive group of the field, and U modulo the center of U is isomorphic to Vn minus 1 and the conjugation action of L, the Levy subgroup, on this quotient is the same as the action on its natural vector space. Okay, and you see here we have 3 types of characters. We have type 1, again with U in its kernel. These are in one-to-one correspondence, again with the irreducible characters of the Levy subgroup, which is a group of, in this case, it's sp2n minus 2 of Q. And as above, we have the type 2 characters, which have U not in kernel, but the center of U in its kernel. And it's, again, easy to see that you have an analogous parabolic subgroup in Gn minus 1 called Pn minus 1, such that the irreducible characters are labeled, of type 2 are labeled by the irreducible characters of Pn minus 1. Type 3, of course, the center of U not in kernel. Well, and here it's not too difficult to work out that, again, these characters of type 3 are in one-to-one correspondence or labeled by the irreducible characters of Gn minus 1. And to obtain this labeling, the so-called Weil characters of Gn minus 1 plays a role, comes in. So I'm going to tell you about this Weil character, of course, but not now, later on. Okay, so, and of course, maybe I can put it here. C, this is, if you take G equal to GUN of Q, and you take V naught, a non-isotropic vector, an isotropic vector, then you have 4 types of characters. And I'm not going to tell you this. But the messages from A to C, you see you get labels or classification of the irreducible characters of these parabolic subgroups. From the linealistic theory, we have labels or classification of the irreducible characters of G. And so we asked ourselves the question, can we restrict the characters of G down to P? And by restriction, of course, we mean we take one character with a particular label, and then we want to find its decomposition and the multiplicities in terms of these labels we have given to these characters. Okay. Okay. So these are the examples. Now let me tell you about the Steinberg character. Okay, so this question about restricting characters, irreducible characters of G down to P and decomposing them is of course much too demanding in this generality. So we try to start with a particular example, and the particular example is the Steinberg character. So let me tell you, okay, let me start with the following. So this exists for any finite group of Lie type. So G, a finite group of Lie type of characteristic P, then Steinberg in 56 has constructed a representation or a character. I'm only talking about characters for simplicity. So there is a distinguished irreducible character of G, now called the Steinberg character and denoted ST index G, so the Steinberg character, such that one of its properties is that its degree is the P part of the order of G. So from the point of view of modular or P-modular representation theory of finite groups, it's a defect zero, P defect zero character. Quite interesting. But this is only a special case of the more general order formula for any group element. It's the value of the Steinberg character is an integer, and it's the order of the centralizer of G, the P part, if P does not divide the order of G, and it's zero otherwise, which follows for general reasons already from this fact. And of course one can also give a formula for these degrees depending on this G. So this is the Steinberg character. So the question is, if G and P are now, as before, one of these classical groups I have described here, can we at least find this? Okay? Okay, let's see. Okay, let's try to do this. So this is again joint work with Gian Bai and myself. So let's try again the symplectic case, Q odd. Well, let's see, the type 1. So we have 3 types of characters, and we want the constituents of each type. Type 1 constituents in the Steinberg character of G restricted to P. So this must be a character of L or of Gn minus 1. This is easy. This is just the Steinberg character of Gn minus 1. So this is quite reassuring, isn't it? Let's look at the type 2 characters. Okay. Well, what do we have? So the type 2 characters are labeled by irreducible characters of a parabolic subgroup of 2 dimensions less. So let's write for the moment psi mu for this type 2 character labeled by this. And so what we want is we take the Steinberg of G restricted to P, and we want to compute this multiplicity. And guess what it is? You take the Steinberg character of Gn minus 1 and restrict it to Pn minus 1 and compute its multiplicity with mu. So this is even better. So this gives you a recursive formula. I mean, this also works, of course, in the general linear group case, and I think it was one of the basic ingredients in the the very good bound on decomposition numbers for the general linear groups given by Brandon, Dipper, and Kleshev. This method, I mean, of restricting not just the Steinberg character, but other characters as well to the parabolic subgroup. So this is a recursive formula. Let's look at the type 3 characters. Okay, so here we found that the constituents of the constituents in this restriction are in 1-to-1 correspondence. Well, so you see, we want labels. The labels are again irreducible characters of Gn minus 1. And so what we find is we have to take a product of characters, omega n minus 1 times the Steinberg character of Gn minus 1, where this is again the Weil character of Gn minus 1. So here again a Weil character appears. But now we have this product. What can we say about this product? So this is good, this is nice, but this is open. Okay, let's look what Olivier Brunner has done. I think in 2 years ago. Let's take the unitary groups. Let's take V0, a non-isotropic vector. And let's put H, the vector stabilizer. So this is then, of course, not a parabolic subgroup, but isomorphic to Gu n minus 1 of Q. But it's a vector stabilizer. And then Olivier has found out that if you take the Steinberg character of G and restrict it down to H, what you get is the Weil character of H times the Steinberg character of H. Once you know that this should be true, it's not so difficult to prove, but you should first observe it. So this is again Weil character of H. So, restricting Steinberg characters to vector stabilizers, we have to compute products of Weil characters with a Steinberg character. This is the message. Okay, so what is the Weil character? Okay. Well, it has a long history. I'm prepared to answer questions. Something is unclear. It has, as I'm going, I'm not talking about the irreducible Weil characters. I'm talking about the real thing. Yeah, but it's okay. So this has a long history. I think it starts with a paper by Bolt, Room, and Wall. Then comes Weil. Then comes Swart. Then comes Howe. Then comes Isaacs. Lehrer, Seitz, and Gerhard. So these are the sources I have found. There may be more. So this is 61, 67, 72, 73, 73, 74, 75, and 77. So these are, all these people have defined one or the other type of Weil characters. Okay, so the Weil character is a character of, well, SP 2NQ if Q is odd. Well, if Q is even, this is not a symplectic group, it's an orthogonal group. GLNQ or GUNQ, and of course also for some simply connected forms of these groups. Okay, so what do I want to tell you about the Weil character? First, I give you the character values in most of the examples. And then I give you a construction. So, character values. So I give you the character values for G. Yeah. Yeah, okay. GLNQ and GUNQ at the same time. So for this we choose a sign epsilon to be 1 or -1. We let G be GLN epsilon Q, of course with the convention that GLN minus Q should be the unitary group. We denote by omega the Weil character of G. So if I say the Weil character, this is not completely correct because there may be more than one, but never mind. At least the degree is Q to the n. Q to the n, so it's not the irreducible Weil character. But it's related to the natural geometry on which this classical group acts. And this degree formula is nothing but a special case of the following formula. So we have a global sign epsilon to the n. We have epsilon q to the n of v and g, where n of v and g is just the dimension of the one eigenspace of the element g acting on its natural vector space. So this is closely related to the natural geometry of the group. Okay? So in particular, if G is GLNQ, epsilon is 1, so it's Q to the dimension of the one eigenspace. The one eigenspace is the set of fixed points of the element G, so it's the number of fixed points of G on the natural vector space. So it's nothing but the permutation character of the group GLN acting on its natural vector space. And for the unitary groups, it's a sort of twisted form of the permutation module, as you can see from these values. But of course, this giving these values doesn't define a character in the first sense. You have to construct the module such that, and then show that the values of the character of this module are as given here. So how can we construct such a representation? I just sketch a construction again in the symplectic case, Q odd, where we have P and U and L as in paragraph 2. Luckily, it's still there. So look at this structure. So we have this subgroup P. If we take irreducible character zeta in U such that the center of U is not in the kernel of zeta, then one knows just from group theoretical structure of this group and little representation or character theory that theta is a character of degree q to the n minus 1. So actually I'm constructing the Weil character for gn minus 1 now. And there are q minus 1 such characters theta. So now this, again, I'm doing Clifford theory. So this is a character of U. And now if you see, and this character is uniquely determined by its restriction to the center of U. Now the group P leaves the center alone, so it fixes every element in the center by conjugation, so it fixes all these characters. So zeta is invariant in P, so this is more or less trivial. What is not so trivial is zeta extends to an irreducible character of P. So it's not completely trivial. And this stage or this part is contained in any one of these papers. Everybody working on such a Weil character at one stage has to show that this character extends to all of P. Okay, and now omega, which is omega n minus 1, which is the restriction of zeta hat to L, which is isomorphic to gn minus 1, is the Weil character of SP 2n minus 1 of Q of this degree. Actually, we get two characters this way in, say, omega 1 and omega 2. Okay. Yeah, there is a natural action of the multiplicative group of the field of FQ on these set of characters, and they come in two orbits, and each orbit gives one isomorphism type of such Weil characters. And omega I splits into two irreducibles. Okay. One of degree q to the n, well, okay, n minus 1 minus 1/2, and the other, so plus or minus. So we get four, for the symplectic group, we get four irreducible Weil characters, but just two Weil characters in the sense I am using them. In the unitary group, you get just one Weil character, but I think q minus 1 irreducible ones, or q irreducible ones. Okay, so I have tried to emphasize a little that this Weil character is somehow related to the natural vector space on which the group acts. Let me give you one more indication that this is the case. Namely, something we do use very heavily in the proof of our main theorem, the multiplicativity of the Weil character. I should of course say the same or a similar construction works for the unitary groups. And for the general linear groups, it's just the permutation character. We don't have to construct it. Okay, see, omega is multiplicative. what do I mean by this? Well, you have this natural vector space on which the group acts. You can view it. You can look at an orthogonal decomposition. So orthogonal decomposition. So this is either a symplectic space, and so you have two non-degenerate subspaces or two non-degenerate unitary subspaces orthogonal to each other. And of course, in the general linear group, it's just a vector space decomposition. And then you have, of course, the direct product of the two linear groups of the two vectors is embedded into the group of the vector space V. And the restriction of the Weil character is just the outer tensor product of the Weil characters on the two vectors. So let me write it here. So this is just G of V1, G, no, okay. Each of these are groups of the same type and they have their own Weil characters. This is what I want to say. So the restriction to such a direct product corresponding to an orthogonal decomposition is the outer product of the corresponding Weil characters, which is, of course, once you know this character formula, completely obvious. And this is one way to prove this, by deriving character formula for the character values. Okay. Very well. So what is the Weil-Steinberg character? So here we use the following notation. G should be one of the following groups. SP2NQ, again, Q odd, of course. GLNQ, but I'm also using now notation, so GN, so G is GN, and this is one of the following groups. GU2N of Q or GU2N plus 1 of Q. The reason for this labeling will become clear in a moment. We take omega n and Steinberg n, the Weil, respectively, the Steinberg character of G, and the product is what we call the Weil-Steinberg character. And I think I have motivated why it could be interesting to look at this product and to find what it is to analyze it, at least if one is willing to restrict characters to parabolic or vector stabilizers. So this is the main theorem by Zaleski and myself, finished last year. So let G be, let's start with GLNQ. Okay? And for any integer between 0 and n, let Pm denote the stabilizer of an m-dimensional subspace of V. Okay, V again is my so acting on V. So this is a parabolic subgroup, of course. Let Lm denote its Levy subgroup, which happens to be GL M of Q, acting on this m-dimensional subspace, times another GL n minus m, but this I have also written Gn minus m for this. So this is the Levy subgroup of Pm. Now we have the following formula: omega n times the Steinberg n is the sum of characters. One sum n for each such m-dimensional subspace. And we induce certain character from Pm to G. And we start with the character of this Levy subgroup. We start with the Steinberg character, M. So this is the character on GL n of Q. And we have an outer product. Here we take gamma n minus m. And so this is a character. So this is on Gn minus m. This is a character of our Levy subgroup. We view it as a character of Pm and induce. And gamma n minus m, of course, is gamma n minus m is the Gelfand-Graeff character of Gn minus m. Isn't this nice? Here you have three distinguished types of characters. You have the Weil character, the Steinberg character, and the Gelfand-Graeff character, all working together in this way. Okay, so this is, of course, in the general linear group. If it were just this formula for the general linear group, I would not be talking about it. Although it's not completely trivial to prove it for the general linear group. So let's also look at the other groups, sp2n of q, q odd, or gu2n of q, or gu2n plus 1 of q. Now you see the reason why I've written these groups in this way, because otherwise they wouldn't have an n-dimensional, well, of course, you see, an isotropic m-dimensional subspace I have to take to get parabolic subgroups. Well, if it's the unitary group, I have to put a q squared here, but this is not really a problem. What is a more difficult problem is that I have to take not the Gelfand-Graeff character, because then this formula is not true. This is a sort of truncated Gelfand-Graeff character, and so this is our theorem. If I have told you what we mean by truncated Gelfand-Graeff character. So this can only be explained by the linealistic theory. And of course, it indicates that it's not completely trivial to prove this. So what is the Gelfand-Graeff character? It is a multiplicity-free character, so it consists of a sum of irreducible characters, one irreducible character for every semi-simple conjugacy class of the dual group. Distinguished for every semi-simple conjugacy class of the dual group, you have a so-called regular character of G, and the sum of these regular characters is the Gelfand-Graeff character. Now, the truncation we have to take here is we take the sum of all these regular characters corresponding to semi-simple conjugacy classes in the dual group whose elements don't have the eigenvalue -1. So we just exclude, we sum over all semi-simple elements in the dual group which don't have eigenvalue -1 on the dual vector space, and then the sum of these regular characters. This is our truncated Gelfand-Greif character. So again, you see the natural vector space, the natural geometry comes into play here. Okay, let me give you some consequences. Of course, we haven't done this in our paper explicitly, but this formula could be used to write down the constituents of this tensor product in terms of the linear Lustig irreducible characters, in terms of the linear Lustig classification, or of the Lustig classification of the irreducible characters. And currently I have a student working on this, just to get him acquainted to this wonderful theory. Okay, so corollary 1. So let's assume that G is not equal to GLNQ. Then this Weil-Steinberg character is multiplicity free. This was quite a surprise, but it can be worked out using this formula. So of course you only have to work for each individual of these summents. A corollary of this corollary, again, it's not true for G equal to GLNQ. Then this Weil-Steinberg character yields multiplicity free projective indecomposable modules in the defining characteristic P. And of course, they are not all of defect 0. So you really get some columns of the P modular decomposition matrix, which consists of 0s and 1s only. So the question in this direction is, of course, decompose omega n times Steinberg n into PIMs. We have not been able to do this. Corollary 3. So here we don't assume that G is different from GLNQ because this works as well. Let V naught be just any vector, then if you take the Steinberg in the natural vector space and restrict it to the stabilizer in G of V naught, then this restriction is multiplicity free. I found this quite remarkable because I didn't believe it in the beginning, because the Steinberg character is really a big, thick character. And this is not true if you look at exceptional groups of Lie type and you take any maximal parabolic subgroup whatsoever. Then the Steinberg character will have multiplicities in its restriction which depend on Q, polynomials in Q. So of course the question or a challenge, is this also true? Yeah, I have been missing one big class of classical subgroups for the orthogonal groups, or SO and Q, so or whatever, plus or minus. So is the restriction of the Steinberg character in an orthogonal group to the stabilizer of a vector, and then you have various types of vectors. Is it multiplicity free? I don't know. I would guess so, but of course, yeah, okay. So let me come to the end of my talk by giving some concluding remarks. Okay, so concluding remarks. Well, one can remove the assumption on Q being odd for the symplectic groups. So this is again in our paper. So same result holds for SP2 and Q. Q even, of course, then we don't have a Weil character. We have to replace it. If omega is replaced by the generalized by the Brouwer character of a generalized spinor representation. This is the one with highest weight, zeros and Q minus 1 in the last position, okay? And in this case, we even can give you the decomposition of the corresponding projective character. At least we can give you a list of the occurring PIMs. In this case, we have omega n times Steinberg n. So this is the generalized spinor representation. It's a sum. J equals 1 to Q minus 1, I guess. Or is it 0 to Q minus 1? PIM corresponding to the highest weight representation, nu j, for nu j is Q minus 1, Q minus 1 j. So in this case, we have managed to decompose this. Of course, we don't know, I mean, we know the corresponding simple modules, but of course, we still don't know how these constituents, which are written there, distribute to these various direct summens. This is still open. B, in recent work with Gian Aachen and myself, we have again considered the symplectic group for Q odd, and we take chi a unipotent character. So this is a vast generalization of the Steinberg character. And we are interested in the restriction to P of all unipotent characters. And so here one question we investigate is, are the multiplicities, so we take chi restricted to P and then the scalar product with an irreducible character in P, are these multiplicities bounded independently of Q? Of course, it's too daring to conjecture that they are all 0 and 1, but I conjecture that there is a bound only depending on the Lie rank of, so on this n for these multiplicities. So this would have very nice consequences for the modular representation theory of these groups in the non-defining characteristic, because then one has a lot of inductive results. And again, it is very relevant if one discusses this question to look at characters, so omega n minus 1 times sigma, where omega n minus 1 is of course the Weil character of Gn minus 1, and sigma is a unipotent character of Gn minus 1. So here, of course, maybe this is not so easy to find these products. But anyway, you see, a similar question occurs. We have done this for SP4, explicitly and for SP6 of Q, because then Gn minus 1 is at most SP4, and we have the complete character table, and we could compute these products, and we found that this is indeed multiplicity free. But yeah, okay. I was told that some of us will go to the pub after this talk. So before that, pleasure. There is the suffer, you know, I'm Protestant. So I give you some ideas of the proof of this main result. Okay? So some ideas. So we want to compute this. And now you see, we have two Weil characters, but they only differ on the classes, on non-semisimple classes on which the Steinberg character is 0. So there is just one Weil-Steinberg character. And it's, of course, it's a uniform character. So you can always write it as a sum of RT thetas, these de Ligne-Lustig characters. And you have some coefficients here, some sine epsilon t, epsilon g, divided by the relative Weil group of the pair t theta, and then a scalar product, which is the character you start with. Let's omit these n's, and then scalar product with RT theta. So we have to elaborate these scalar products. And you will see why it works in this case. Because now we can move the Steinberg on the other side. And now one knows that this is an induced character, namely the character induced from T to G. And now one uses Frobenius reciprocity. One has to restrict omega to T and look at the theta. So this is one of the main ideas. And now use the multiplicativity, okay, use this property, which is called multiplicativity of omega to compute this. Okay, so this is easy, and then a big thing is to show that if this is non-zero, and we only have to consider those, then T stabilizes an isotropic subspace. And for this we have to work very hard. And then finally we can put everything together. I think I have 1 minute, or maybe 2. Okay. I presented this method because, of course, it has some more potential. So using this method, so this is the last of my remarks, using this method, we are now, so we is again Alex Zaleski and myself, compute products of the form sigma times Steinberg character of G, where now sigma is a generalized P modular character. So, for example, if mu is some highest weight, we can have sigma the character of the simple module with highest weight mu, or we can have this so-called Wong character. So generalized characters introduced by Wongs, which are generalized Brouwer characters. one character associated to a highest weight, and which are defined on one fixed maximal torus. Thank you for your attention.